Okay, the next person speaking is Andre Bedard from Michigan State University.
Good morning, everyone. My name is Andre, and I'm at Michigan State University. What I would like today is to discuss a little bit about the spectroscopic methods and how they appear in the recycling. I'm not an expert in spectroscopy, but I've been interested in recycling for about 7-8 years. I'm more in materials processing, composite processing, but I've been exposed to spectroscopy through my colleagues here. Nalin Kumar, by osmosis, I've learned a bit about these techniques. Nalin is president of UHV Technology, and he's coming up just this month with a new product for sorting materials based on X-ray fluorescence. Marcos Dantus is in chemistry at Michigan State, and he has developed a new technology called CARS and supercars for sorting. That stands for coherent anti-Stokes Raman spectroscopy, if you know the technologies, for sorting materials remotely. And then Randy Knibbe is the vice president of plastics at Padnos. It's a local recycler, the largest recycler in Michigan. And they have, in downtown Grand Rapids, they have a facility of about 12 acres where they sort plastics primarily from post-industrial waste. So I learned quite a bit about technology involved in these processes. So this is our slide, if you want, that I often use in presentations for representing how a recycling facility operates. On the left-hand side in the blue box, what you have is a material that might be coming, for example, from post-industrial waste. This is the kind of waste you get, for example, from trimmings and plastics from manufacturers, tier 1 suppliers, where they make dashboards or parts for cars. Then they're left with significant trimmings. It's relatively clean stream, and that's where many companies make a profit in recycling plastics. The plastic is often black, unfortunately, but they test for that. And then there's large volume of it, especially in Michigan, of these plastics. And then you can also look at that as being the materials recovery center, where things become very mixed here. And on the second row here, we have the inputs. So these are different mixed glass, plastics, papers. And spectroscopic methods play a unique role in these centers where they can sort and classify materials. So, and once you have as many speakers as Brian has addressed before, once you have the stream, so it's important to know exactly what you have, and the more the pure the stream is, the more profit or the more value you can add to the materials. So, and then you can direct it to an appropriate processing techniques. And if you can separate things as very cleanly also, so that gives rise to new manufacturing processes. The opportunities are especially in metals, but also in plastics, where if you have, instead of mixed aluminum scraps called Zorba, now you know exactly what kind of aluminum alloys you have. Then you can have, instead of a pile of mixed aluminum the size of the building, now you have smaller piles, which is 6,000, 6,000. One is good for casting, the one is structural. Then you can locally make small processes to reuse these materials directly on site. Same thing happens for plastics, where you can remake, for example, filaments for 3D printing devices. So we'll do that very quickly. So many speakers, as Brian has talked about, how little plastics will recover here, and it's challenging to identify materials here. Current techniques, mechanical recycling, work well if you know sort of the feed, what you have there. But if you don't know what you have, spectroscopic method is probably the only techniques that allows you to do elemental analysis, to know what you have exactly. As an example, I have a prop here that I brought on my way here. So I have 2 plastic cups here from coffees. One is made of polystyrene, it's white. The other one is polypropylene black. This one has carbon black. This one, titanium dioxide for coloring it. If they were both black, you could not sort these in current equipment used commonly. Okay, so just a little prop for today. And this is an illustration of spectroscopic method, very briefly. So they're distinguished by the source. You could have X-ray spectroscopy, infrared spectroscopy, etc. So they're also classified about how the material responds to the techniques. So it could be reflectance, absorptions, transmissions. So then you go to, for example, FTIR, Raman spectroscopy, LIBS, which stands for laser-induced breakdown spectroscopy. Hyperspectral imaging now is making an appearance in recycling, which is you stack images and you captured at different wavelengths. X-ray fluorescence is showing up, and mid-range infrared spectroscopy is also showing up in recycling. And this again, so this is what's being used currently. So it's a little graph I made just before coming that shows what's going on right now in many of the materials recovery systems. So you have near-infrared spectroscopy used for sorting plastics from cardboard, for example, and different materials. You can also, there's also visual scanners that will sort materials based on color, for example, very quickly. And these, like Brian showed, they go on a belt, very high speed. There's many videos online on YouTube if you want to see that. It's very impressive. Puffs of hair show the material being ejected in different bins. And then they are often combined with image analysis for shapes, characterizations, etc. Black plastics like this, if you have different materials, you cannot sort them out right now, so on current equipment. So, and there's rapid changes going on in sorting technologies due to fast computers. You'll see examples of that now. And also large storage capacities for example, hyperspectral imaging requires significant storage, a lot of processing power, and you have stuff coming on a belt at a few meters per second. You have to sort them out. It's now possible to do that. And we have sensitive detectors being online, new cheap lasers, cheap meaning $50,000, $60,000 for 2-watt lasers, for example, that's megahertz capacity. Machine learning is making an impact also now. And we're a long way, for example, of the 1980s, where the only sorting method we have was to use electromagnets to pull metals out. But that led to a revolution in the steel industry also at that time. So many industries were built on using recycled material and reprocessing locally, while the typical ways were going downhill with competition from Asia, for example. So this is what's going on right now. This is an approximate timeline, so I didn't have time to play the historian and give you exact things. This is what I understand from talking to people, is that about 2005, 15 years ago, optical sorters started appearing in MRFs. So, and they can scan material very quickly. These are optical scanners built in with NIR. Then about, I would say 6-7 years ago, flake purifiers based on Raman spectroscopy can sort materials pretty well. So you have a big bin of material, the little flakes that Brian showed, and then they fall down like a stream, and then you have puffs of air that will eject the flakes and sort them out based on composition and colors. So, and then they work well, but they're relatively slow right now because they're relatively slow. And now, about 3-4 years ago, optical sorters are commonly used right now and based with combined with NIR. Hyperspectral cameras now start appearing, and they can sort black plastics, these cameras now. So this has become an issue that if you want to invest on hyperspectral imaging now, you can sort these issues right now. And something appearing now, about 2-3 years ago, I met Dr. Horowitz. He's the president of AMP, and he was a recent graduate of Caltech, if I remember right. And he was trying to promote the use of robots with AI and imaging for sorting material to supplement humans in machine. And they were beginning to sell the robots. And nowadays, I have a slide that shows that robotics is becoming increasingly more used in sorting material. And 2019, we have XRF coming online along with cars and supercars. Just talking about the recent spread of robotics and recycling, 2 years ago, there were only 6 robotic stations reported in the US, and now there's about 80, and about half of them are in MRFs. And they're all based on vision system combined with artificial intelligence and machine learning for sorting and identifying materials. They're slow, they're different than the optical scanning methods, but they supplement human sorting if you want. So they work with human interactions for picking out things like metals or needles, etc. And much more is possible for these systems if you combine that with spectroscopic method, for example. Okay, so, and now switching topics a little bit, I would like to talk a little bit more about 2 technologies used, more specifically X-ray fluorescence first. It's an old technology that is undergoing a revival now. The way it works is relatively simple, is that you have an X-ray tube, typically it's going to be a beam, that an X-ray beam that will irradiate a material. You get a response from that for material at lower energy or longer wavelength. And this response can be read, and you can classify materials based on that. It's used in the lab often for sorting materials, glass, plastics. And it's also used currently in sorting facilities. There's handheld XR gun, but you have to pay $30,000 for these machines. They use them for sorting metals, for example. If you have a lot of scrap metals, you want to know what it is, you can use an XRF gun, but recycling centers typically have 1 or 2 of those. So it requires an X-ray generator and a solid-state detector with that. And typically it's done in vacuum or very close to the surface, and you get a reading like this. So, and this is what's going on now. So you have a belt with XRA, so you have some waste material or scrap that passes at high speed on the belt. And UHV designed a new radiation source that is linear, so can irradiate the whole belt. And there's vision combined with that corrects for the distance from the detector, and then it can account for the attenuation in air, because XRF is often done in vacuum, so because of significant attenuation of the fluorescence in air itself. So now you have an example of combined high-speed computers to correct for the attenuations, material coming on the belt, X-ray fluorescence, a new design of an X-ray tube that irradiates a belt of material, and you can sort the material very precisely based on its composition. It's used for metals now. And same thing can be used for plastics. You can identify the fillers, the composition type of plastics that can be used. And then at the end here, you have the trap belts, for example, the trap doors, and then things just fall with the controllers. The material just gets sorted. The scraps get sorted based on the trap, or you could have a puff of air that would eject the material like that. So, and this is the 2019 patent, for example, that shows the belt on the bottom, the vision system that identifies the materials, tag them. The X-ray tube is shown there also. They raise the material correction. It's done for attenuation. And then you read the spectrum, compare with the database using machine learning, identify the materials, process it, and sort this out and send that to the appropriate bin. It's a very fast process now. And this is a two-lane small XRF sorter shown here that was developed by UHV. On the left-hand side is a controller. You can see the belt, the end of the belt on the right-hand side. And this is the sorting. We can see the Home Depot buckets on the bottom for blind tests. So they just label material and pass it through. So this was the development phase. And the material goes through and just get ejected. With this one has little paddles that kick the material in the appropriate bucket instead of trap doors. This is the scale-up process for XRF, and you can see, so this is the larger system developed by Ares. Ares is one of the large equipment suppliers, so they partner with UHV to develop this. This was developed under ARPA funding or DOE funding, and you can see the scale of the system by the little operator there standing there. So it's about, probably, I can't read the data, it's about 30, 40 feet long, roughly, in terms of sorting. So. And this is the pilot plant installed in OmniSource. OmniSource is one of the largest metals recyclers, scrap metal recycler on the East Coast. And they can process right now about 30 million pounds per year of materials sorted very precisely down to the alloy grade. And the plant scale up right now is about 200 million pounds per year of scrap metals sorted. And this can be applied for, this is used primarily for metals, sorting aluminum alloys, magnesium alloys, etc. So stainless steel, but you can apply that for plastics also. And again, this is a larger belt, 60-inch irradiation belt for sorting metals that also works well. The next topic I just want to discuss a little bit in terms of what's upcoming in new technologies would be CARS, or coherent anti-Stokes Raman spectroscopy. So the way to describe that, according to Marcos, this is all done by Marcos Dantus at MSU, is that it's Raman spectroscopy on steroid. That's how he looks at it. So it's very fast. It's thousands of times faster. It's more accurate also than Raman, essentially. Raman can be slow to sort material. This is much, much faster. In his research was developed by the Department of Homeland Security for detecting trace explosive in the atmosphere on bags, etc. But it can be used also for sorting materials very precisely and to know their chemical composition very accurately. And this is an example of, this is one of his postdoc here. This is a little video that shows that as he breathes on the sensor, so you can see the CO2 peaks showing up on the left-hand side and the O2, and you can see the signature coming up for the signals as he goes and he breathes on them. So it's very accurate and very fast also. And this was done about 8-9 years ago. Okay, so, and this is on loop, I'm sorry. And this is another one of his students, that what there is that on the left-hand side is a computer, and there's a little alarm with an exclamation mark that tells you, okay, so we've detected that chemical compound, and it becomes white. And then the student is moving a little tray with different material that have been contaminated, and he's looking for a contaminant here. So as he slides the tray, and then when the chemical is identified, so there's many different substrate, the chemical, there's an alarm that's ring. So it's very precise and very fast. It's done real time, actually. So, and then there's different materials, and he has like little baby socks there. One is contaminated, the other one is dirty. There's a sugar, so he has different materials he slides through, so we don't hear. There's wood, so it will detect specific contaminants or specific compounds very accurately, very rapidly also. So And we can see, so it becomes red when it detects the contaminant on the little sock there. So, and this was done quite a while ago, about 6 years ago, with a relatively slow laser. Now lasers are about megahertz scale in speed, so this was a kilohertz laser. So this is a lot faster. Today it's possible to do things much faster. So, and this is the concept, for example. So this is how it's done in the lab at the bottom. So you have the table with the optics and the mirrors and the grates, and then you have the source and the processor. But it's possible to very quickly assemble a working prototype that could be very relatively compact now. And this is an example of what can be done with a 2 megahertz laser. Before it was a kilohertz laser. So now you could, for example, acquire 20,000 different spectra, so 20,000 dots, and each one of them is an average of 100 pulse. So the accuracy is very high, and then you could scan a whole field with dots or raster an image like this. So if you have, you can scan images on skin or surfaces because the frequency used is eye safe or skin safe. And then you can identify compounds in a very small area, but this is rasterized to a very high definition. So, but you can move the lasers using mirrors, etc. So scan very large area very rapidly also. And these are just different chemicals identified on different substrate. Supercar stands for single pulse. And then the acronyms, I can't remember exactly what the UPER stands for here. I'm sorry. And then this is new. So this is a picture that Marco sent me just before coming here of a new laser that he acquired in his lab. So, and if I remember right, it cost him $60,000, the laser, and it can be used for doing all these detection techniques very rapidly. So, and it's down there in red, the yellow, and the rest is the optics. So you could rearrange that very rapidly to make a car's sorter, which is very, very rapid and could sort plastics on the belt coming very, very rapidly, or flakes, for example, like the flake sorters use. So now that leads to probably making new opportunities in tackling problems, for example, like automotive shredder residue. I'll put a slide there because I'm aware of this problem. So in when you have a car, for example, at the end of life, your car, they pull the tires off, they pull the fluids, they pull everything they can retire. Then your car is sent to a shredder. In Michigan, there's about probably, I know that Panos have 5 shredders in the state roughly, and then there's others that will have different shredders. Your car gets shredded down into balls the size of your fist roughly of metals, and then they sort them out mechanically and using electrostatic separation, magnetic separation, etc. So it's highly automated. And what's left at the end, after you sorted all this, is you're left with fluff or ASR, and that's sent to the landfills. So, and they send hundreds of tons of that stuff regularly to the landfill. So on the landfill in Michigan, at least, use that for capping the landfill. So it's good material, it's fibrous, so you can use that, but it's made of all sorts of mixed plastics, electronic things. So if we could sort this out, that's a big environmental problem also. And down here, I listed 13 common. And the challenge is significant in those in sorting these flakes. And the plastics show up as flakes in this material. So, so that leads to new opportunities. Just recently, to finish my presentation, I just want to mention that I was just reading last week, there's a white paper from the World Economic Forum where they identified in Michigan alone about 7 billion of opportunities for in tackling or getting involved in technologies associated with what's called Industry 4.0, Manufacturing 4.0. We have been hearing quite a bit about that recently, and essentially it's the combination of Internet of Things, big sensors, large storage, big data, fast computers, robotic automation into enhancing manufacturing. And for the car industry, to identify, for example, augmented workforce with virtual reality, for example, collaborative robots, and we saw that in recycling. There's some opportunities there too. Metal 3D printing is one in automotive industry, but also digital twin technology, which is you make a duplicate in the computer of a factory, and you can use that for predicting, for example, maintenance, what will happen, control of systems, etc. So recycling industry is also highly automated and also highly mechanized. So if you go to a MRF or a recycling facility, you'll be very impressed by all the technology involved in these systems. So it's very impressive. It's highly automated. It's also labor intensive, it can be. And I do think that significant progress exists if we can combine these new sensors that are appearing. There's much more out there in terms of spectroscopic sensors that be combined with all these new technologies like hyperspectral imaging, XRF with fast computers, large data to sort this material. And we might be making some ways in tackling this problem. Thank you.
Hello, Yelena Khan, Radical Plastics. The X-ray separation, not on?
Yes.
Yelena Khan, Radical Plastics. Question about X-ray screening plastics. Will it damage plastics too? Will it cross-link them or break them down to radical?
As far as I know, no. The exposure is very, very rapid. I don't think it will damage them, but I'm not 100% sure, but I would doubt it. Yeah. Okay, thank you.